Welcome to this explainer covering GEM in the real world. Today, we're diving into Series 5, Episode 2, Why Roads Crack Too Soon. We're going to apply a very grounded, forensic diagnostic lens to one of the most fundamental mysteries of infrastructure failure. I want you to picture a perfectly smooth concrete road surface. A heavy vehicle passes over it. Nothing seems wrong at all. But what's actually happening right beneath that surface?
Well, this brings us directly to our core thesis. A road does not begin failing when the crack appears. The crack is the receipt. Take a moment to think about that. By the time concrete physically breaks open at the surface, the real story has usually been unfolding beneath it for months and sometimes even years. The damage you're finally seeing? That's just the final transaction.
The absolute crucial point we need to understand is this. The road does not fail when it cracks. It cracks because the route has already failed. We really have to stop looking purely at the visible damage and start examining the unseen history of the material itself. Concrete failure, at its core, is fundamentally a route failure. So what exactly do we mean when we say route? Most of us naturally assume concrete is just a recipe. You add your cement, some water, aggregate, maybe an admixture, and you just wait for it to get strong. It sounds so static, doesn't it? But in the real world, concrete is not a recipe. It's a route. Notice how that exact same recipe can behave entirely differently depending on its journey. We're talking about how it moves through unpredictable temperature variations, mixing energy, transport time, and curing conditions. Here's the truth of it. Concrete is not accepted because it sounds strong on paper. It is accepted only if the route can survive the world it enters. Theoretical strength means absolutely nothing if the mix can't survive the harsh, practical constraints of real-world transport times, highly variable aggregates, and drastically changing weather. In GEM, we frame this hidden failure using a very specific diagnostic concept called coherence debt. So what is coherence debt? Simply put, it's stress the system has encountered but has not yet recovered from. In concrete, failure actually begins the moment the material can no longer recover the physical geometry it was supposed to hold. It is the true microscopic origin of a failure. Let's zoom in a bit closer at these unseen debts. On a microscopic level, these debt markers are quietly accumulating way before a crack ever shows up. We're looking at things like thermal cycling, moisture imbalance, tiny microcracking, bleeding, and segregation. These are silent, invisible stresses that are basically storing up potential energy beneath the surface, energy that will inevitably demand to be paid. If we trace this chronological journey, we can see exactly where that debt piles up. It starts with mixing, then transport, placement, curing, the introduction of real-world stress, and finally, validation. By mapping this out, we can clearly see where the material is at its most vulnerable. Even a slight error in transport time or a tiny failure in curing essentially locks structural weakness directly into the material's history forever. And because of this strict timeline, we have to look right at the very beginning. Concrete starts proving itself before it becomes hard. The fresh state is not just some mere inconvenience we have to get through. It is the first and honestly the most critical warning signal. If a fresh mix opens too fast and starts collapsing, it's already failing. The engineering reality is crystal clear here. Concrete does not prove itself when it becomes hard. It starts proving itself while it is still trying not to fall apart. Early stability is absolutely everything. Specifically, we're talking about avoiding bleeding, where water unnaturally rises to the top, and segregation, where the heavy aggregates sink to the bottom. If the mix can't hold its geometry in the fresh state, it's already drowning in debt. Now, this brings up a really fascinating dynamic in the industry. There's this huge assumption that workability and early strength are opposing forces. Basically, the idea that if you want your concrete to be workable for a long time, you have to sacrifice its early strength. But a truly coherent route balances both of these through high dispersion efficiency and carefully controlled rheology. The fact is, workability and early strength were never drawing from the same account. A properly designed, mathematically stable process route allows for extended workability without ever sacrificing that early performance. Honestly, when one seems to drain the other, it's usually just a glaring sign that the process route itself was badly designed from the start. Moving on, let's take a look at Section 1, Concrete Route Check, which serves as our diagnostic framework. So, rather than just relying on your standard isolated lab validation, Route Check is a preventative, real-world framework designed for identifying risks. It maps out the actual reality on the ground, charting out risk corridors, pinpointing evidence gaps, establishing firm claimed boundaries, and outlining the exact next validation steps. It makes sure we aren't just blindly trusting theoretical recipes.
Using this requires a total paradigm shift in how we think. The question is no longer what is the mix, the real question is this route stable enough to validate? We absolutely must rigorously interrogate the overall stability and repeatability of the route itself as it faces all of its real-world disturbances. Because ultimately, what does a civil engineer actually care about at the end of the day? They care about real-world validation. Can this material be produced and placed? Can it be corrected and properly cured? When it's stressed by heavy traffic and severe weather, can it actually recover? A successful mix must open, hold, and descend without collapse, delivering repeatable, defensible results every single time. When we fail to validate that route, we get exactly what we see on our highways every single day. The crack is not the failure. The crack is the evidence. When water finds its way in, when heat expands the material, when traffic constantly repeats stress, and when poor curing preserves internal weakness, that hidden route failure transforms into visible surface cracking. The debt is finally being collected. Let's apply these diagnostic questions directly to our civil engineering reality. Ask yourself, what stress is stored? Well, that's thermal strain, shrinkage, and traffic. What recovery is delayed? That would be proper curing and basic maintenance. What cost is exported? Obviously, future repairs, massive public disruption, and safety risks. And finally, what collapse is already being paid for? It's that invisible structural coherence debt we've been talking about. Which brings us to a really profound summary of what our actual goal is. Good infrastructure is not the absence of cracks today. It is the presence of recovery routes tomorrow. True coherent engineering means building infrastructure that is actively designed to recover from the real-world disturbances it is inevitably going to face. As we wrap up this analysis, I want you to keep this thesis firmly in your mind. A road does not fail because it forgot how to be hard. It fails because the route that made it hard could not survive the world it entered. Concrete is never just a static material sitting there. It is deeply and inextricably tied to its environmental journey. I'll leave you with this final thought, and it's one that should fundamentally change how you view the infrastructure all around you. Next time you're driving over a broken, damaged highway, ask yourself, did the road fail when it cracked, or did the route fail long before the crack ever appeared? Thank you so much for joining me for this explainer. Keep questioning the unseen structures around you.